Hello everyone. I'd like to talk about multi-class classification in the Softmax function so that you have a reference to go along with what we did in class. And I'm also going to take it a little bit further with the math for those who are interested. So with logistic regression, we were addressing the binary classification problem. So like telling cats from dogs, for example. But now we want to generalize this. I'll do multi-class logistic regression where we want to learn one of many options. So for example, with the digits, I may have actually 10 options, 0 through 9, for the digits in base 10, if I have images of those in the MNIST dataset. So in the binary case, for logistic regression, we had an activation function, which was the logistic function. So that was 1 over 1 plus e to the negative u. So I'm writing this in LaTeX here. Or LaTeX, I guess I should say. I'm trying to make that come out big. That's not really happening. Okay, let me do an H3 here. That's a little better. Okay, so that's the logistic function. And then we also had a loss function, which was the logistic loss, which I won't repeat here for the moment, but you can go back and look at that. Okay, for multi-class logistic regression, we're going to have another activation function, which is actually a generalization of the logistic function, which is called Softmax. So let me define this here. In the case of multi-class logistic regression, we actually have a vector u as an input. So u is now a vector. And what I would say is that the softmax, maybe we'll call it sigma sm of this vector u. Okay, just make sure that's showing up okay. Sigma underscore sm, I meant to say, of vec u. Okay, there we go. So the softmax function on a vector at a particular component I is equal to e raised to ui, so the ith component of that vector, raise e to it, and then divide that by the sum over all the other components, including I actually. So maybe I say I have an L-dimensional vector. I want to divide that by the sum of e raised to uj for all the other components. So this is the softmax function. I divide, let me make that nice and big here. I raise e to the component of the vector, and then I divide by the sum of e raised to all the other components. Okay, so that's the softmax function. And so I can ask myself, okay, what does this do? And I had the examples of the digits here. Let's say I had some model that was outputting all of these numbers here. And these you can interpret like log probabilities. So I have one number for every class, 0 through 9 here, that the digit could be. After I run this input through the softmax function, so I raise e to each of these and then divide by the sum of e raised to each of them, this is what I get. So you notice that the softmax really emphasizes the values that are relatively larger. So that e really blows up, the e to the whatever really blows up the largest things. It makes them stand out even more. The other thing we notice is that each element of the softmax is non-negative, because e raised to anything, whether that's a positive or negative number, it is non-negative. An exponential can't be negative. And then we also have that each, or the sum, the way that we've defined this, the sum of all the elements is 1. So we can interpret the input to the softmax as log probabilities, and the output of softmax as estimated actual straight up probabilities. So that's the interpretation that we're going to have of the softmax, right? And here's what it looks like. Okay, now I need to define a loss function on top of the softmax, just like I did for the logistic function and where I had a loss. So let me go ahead and do that. There's something called binary cross entropy that I'm going to use as the loss. Oh, actually, one more quick thing I need to do before that. Okay, so I have the softmax here, and I have the output of the softmax. But I need some kind of ground truth answer. So I need to know, okay, this was actually supposed to be a 3. So before, when I was doing binary classification, I had my input x and my output y, and y was either 0 or 1. But now, for multi-class classification, we're going to have a multi-dimensional ground truth y that we aspire to. So I'll define something called has a funny name, one hot vector. So I'll call it y superscript k as the following. So I'll say, okay, this one hot vector y superscript k is equal to, well, it's going to be 1 if, so I look at, let's say I look at the ith component, so it's a vector, I look at the ith component of this vector. That'll be a 1 if I equals k, or a 0 otherwise. Okay, let's see if all this LaTeX came out right. Nope, because I need the $sign over there. Oh, come on. I meant to say begin array, and of course I have to end the array. So end array. There we go. Okay, so this is my one hot vector. Now, okay, this is a fancy name that that machine learning people came up for something that's very well known in math, called the standard basis vector in Euclidean space for the ith dimension. But okay, we're gonna roll with what machine learning people call it, and call it the one hot vector. Sounds a little bit more exciting, maybe. Okay, so I need to define a loss, and actually this table up here is getting a little cramped, so maybe I'll just say it's called the binary cross entropy loss, but I'll use a little bit more space down here to actually define it. So the binary cross entropy loss between an input, u to the softmax, and a one hot vector y I k is defined as the following. So it'll be the sum over all dimensions of y I, or the vector y ki, so the ith component of the one hot vector, times the log of the softmax of u at the ith component. Okay, so let me see if I got that. So summing over each component of, so these are both vectors, the one hot vector yi k, or the one hot vector yk, and then the input vector u, which that's an input vector to the softmax, will also be outputted as a vector. So I sum through both of those vectors, and I do actually what I'm computing here is a dot product between the one hot vector yi and the log component-wise of the softmax. And actually I need to add also say BCE of u, the vector u and the one hot vector y is actually the one thing I need to add is it's the negative of all that. Okay. So, okay, I think I got it. All right, so the binary cross entropy loss between the u and that one hot vector is the negative sum, the negative dot product here between these two things. And so, okay, where the heck did this come from? So I want to give a quick mathematical aside here as to why this loss function actually makes sense to compare the one hot vector to the output of the softmax. But first, I'll note that like the logistic loss, the binary cross entropy loss is 0 if and only if the outputs of the softmax exactly match the one hot vector. So we look at this, and actually the only terms that matter are the vector where it's 1. So as an example, you know, y6, you know, the one hot vector y6 would look like 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6 has got the 1, 7, 8, 9. So that would be 0, 1, 2, 3, 4, 5. Oh no, 0, 1, 2, 3, 4, 5, 6. There we go, I got it. So I should have 10 dimensions total in this array, and the one at index 6 should be a 1. So that's my one hat vector here. If I look at the dot product here, the only term that's going to matter is the one at index 6. All the other ones are 0. So if I look at that, all right, well, that's just going to be a 1 for the yi there. And this is going to be, if the output exactly matches that, then this is going to be the log of 1, which is 0. So 0 times 1, that term drops out too. So this is 0, if they agree exactly. Otherwise, if this is a little bit smaller than 1, then I'm going to have the log of a number that's a little bit less than 1. That's going to be negative, a negative number, but then I negate it here, so this loss actually goes up. Okay. But how the heck did I come up with this anyway? So I do want to just a quick aside here, and I'll say I'm going to define something else called the entropy of a probability mass function. So what we have is you know, probability mass function is just, so I'll say PMF. So I'll just note that a PMF is an array of possible outcomes with their probabilities. So as an example, you know, I could have, you know, maybe I have the possibilities 0, 1, and 2, and maybe 0 has a probability of 0.2, 1 has a probability of 0.5, and then 2 has a probability of 0.3. That would be an example of a probability mass function. Okay. So in this case, I have 3 events, 0, 1, and 2, and that's what their probabilities are. So, all right. The entropy then of a probability mass function is defined, actually we use the letter h for some reason. So I'll say h, maybe I'll call the probability mass function x. So I'll say h of x is really actually what's called a random variable. H of x is the sum over all the possible outcomes of the probability of that outcome, or sorry, of the the probability of that outcome times the log of 1 over the probability of that outcome. Okay. So what I'm saying, you know, in the example here, what I would say is that, okay, the entropy of this would be, and let me use log base 2 for now, actually. So the entropy of this would be 0.2 times log base 2 of 1 over 0.2 plus 0.5 times log base 2 over, or log base 2 of 1 over 0.5 plus 0.3 times log base 2 of 1 over 0.3. Actually, let me just go ahead and compute that in code here. NumPy has a log 2 in it. So I go ahead and, well, I should import NumPy, of course. I would have done that down here. And I see that the entropy of this is about 1.5. Okay, so what does that mean? Well, the entropy is a measure of the expected number of bits that I should use in an optimal representation of my random variable. So to explain this, I really have to go back to 174 and look at the Huffman trees lab that we did. So remember when I was saying here, okay, we can create a code for letters that does not use the same number of bits for every letter. What we're going to do is use fewer bits for letters that occur more often. So like E is a very common letter. We're only going to use 3 bits for E. But Q is not a very common letter. We'll use what? 10 bits for Q. All right? But that doesn't happen very often. Okay, so what we say here, that the least likely thing here is the value 0 in this example. That only occurs 1 out of every 5 times. The log base 2 of 1 over 0.2 is, let's look here, a little bit over 2 bits. So this is the least likely thing. It actually requires the most bits to store. But what we can interpret the entropy as an expected number of bits to take. So the average number of bits I'm going to take. So I do a weighted average by the probability of occurring. This doesn't happen too much. When it does happen, I have to use more bits than I would for this one, right? Log base 2 of 1 over 0.5 is actually just 1 bit for this event. So that happens more often, and I don't have to use as many bits. This happens less often, I have to use more bits. And so it's a total measure of information of my random variable. It's how do I capture my random variable in some kind of bit representation. Okay, so that's called the entropy. And so cross entropy, actually one thing I'll do to this, I'll just do a little log thing here. The log of 1 over something is actually the negative log of that. So what I'll do is I'll do the 1 over that, take the negative out, and I have an equivalent definition here. This is another definition you can give of entropy. As you notice, I'm getting a lot closer to matching the definition of cross entropy. So cross entropy is very similar. If we interpret here, so Y is like a probability distribution. It's actually kind of an ideal probability distribution if we're guessing one class. So this one hot vector says, okay, my probability mass function puts all of my mass on this one event and no mass anywhere else. Actually, this whole thing has an entropy of 0 because the only thing that ever happens is this. So we don't need any bits to store the outcome of this one hot vector if we interpret this as a probability distribution. Okay, but what we'll do is we'll say, okay, assuming this probability distribution, what happens if I actually use the number of bits from my softmax output? So I could say, okay, I have another probability distribution, which is my best attempt to match my ideal one from the one hot vector. What would happen if I actually used the probabilities from not my distribution, but I used the values, the probabilities weights from another distribution? So this is called the cross entropy. It's a measure of the information loss between 2 different distributions. Basically what it is. So that's where it comes from. There's actually a little bit of information theory going on in the background here. All right, so let me pause for a second and let that sink in, and then I'll wrap this up.